Good afternoon. Welcome to Transfer Phenomena in Bioprocess Engineering NPTEL course, week 4. Today we will discuss about the fluid flow measurement. Even the previous class also we discussed the continuation of, then we will discuss today. So, the last class we discussed rotameter, venturimeter, but this class we can discuss the orifice meter. So, what is this of orifice meter? This is also one more the flow measurement device. So, the orifice meter measure the flow by restricting the fluid path. So, resulting finally is a countable pressure drop that correlate with the velocity. So, they are saying that pressure proportional to velocity. From there we will get they get a pressure drop, from there the flow velocity will be there. So, then as a fluid flow through the small orifice, what is happening here in the opening small orifice? So, the kinetic energy get increases. What is the kinetic energy? Normally we write kinetic energy of m v square, or we will write a v square by always write a 2g. So, this is a kinetic energy. So, kinetic energy increases at the expense of pressure energy, here the pressure energy is a P by rho g. So, finally we will get the resulting in the differential pressure P1 minus P2. So, the kinetic energy get increases, and then by expense of the pressure energy P by rho g, and then finally the result is the differential pressure P1 minus P2. So, orifice meter here, the figure given here, the first, this is the direction of flow, first direction of flow this direction, not this direction, it is a direction of flow. Here the upstream, there is upstream here, then the pipeline and orifice plate, just see here orifice plate, the plate is here orifice plate, there is a opening hole here, that is a orifice diameter, we call as orifice diameter here, then the another portion is a downstream, and then this point, the exit, exactly the point is a vena contracta, the concept vena contracta here, and then this will be connected with the U-tube manometer, like that is a pressure measurement device. So, first what is orifice plate here? It is a thin flat plate concentric sharp edged circle hole with a diameter of DO. So, the diameter is a DO, that is the orifice diameter, but a very sharp hole. So, thin flat plate, the concentric, the sharp edged circular hole with the diameter of DO, orifice diameter. So, next one is for vena contracta. The point of downstream, this side downstream of the orifice plate, where the fluid stream that reaches the minimum cross sectional area. So, the minimum cross sectional area, there definitely the velocity is a maximum velocity, that is called V max, we always write as a V max. So, any type of the flow here, the velocity is a maximum at center of point. So, V equal to V max, we discussed so many times, V equal to V max, wherever V max is there, that the shear stress is a 0. Then the wall, if you take the wall, the velocity is a 0, but the shear stress is the maximum. So, the minimum cross sectional resulting the maximum velocity and minimum static pressure, that called as the vena contracta. So, another point, the pressure tapes, it is installed upstream point 1, that is called a point 1 here, this point 1, and downstream at the vena contract point 2, So, the pressure difference, what we write here, P1 minus of P2, that is the pressure difference. So, once again repeat here, first is the orifice plate, that is a very small diameter, we called as a DO. Then the vena contract where exactly here, that is a downstream side, exactly the point of the downstream, where the point of downstream, the orifice plate, where the stream reaches a minimum cross sectional area, but a maximum velocity, and again minimum static pressure. The pressure trap installed at two places. One is for to point 1, we call it the point 1. The another point is the downstream side here, that's the P2. So what is the pressure difference here? P1 minus P2. The orifice meter here given here. So the Bernoulli equation, of course we know Bernoulli equation, it's a combination of pressure energy B by rho G, then V square by 2G. One is the pressure energy, then other one is for kinetic energy, then potential energy. We always write a rho G Z1. So same way equal to, if you write 0.2, then P2 by rho G, then V2 square by 2G. It's a Bernoulli equation for this one. Then the last point is the rho G Z2. So if since is a horizontal, pipe is a horizontal, this one, then automatically we'll get a 0, this one. Then only we have the pressure energy, then kinetic energy. So 0.1 we write 0.1, then 0.2 we write a P2, then V2 square by 2G. So then after modification, then always we can write here, this equation will come, velocity equation. How? Again you have to use the continuity equation. Continuity equation, of course we know rho 1 V1 A1, rho 2 V2 A2, that's the continuity. If densities both are same, the density is the same, then we can write V1 A1, V2 A2. Then again the A1 is expanded in terms of pi by 4 d square, pi by 4 the cross sectional area d1 square, and again here pi by 4 d2 square. So we have to expand here, but since the V2 square, it goes as a d2, d1 power 4, then d2 power 4, like that will come, because the velocity is, we are replacing velocity here, this equation we are replacing here. So after a modification we get the diameter ratio. What is the d? Beta is the diameter ratio. Beta is the diameter ratio. We already discussed. Then the density, and the C naught is the orifice coefficient. Whatever orifice this one. Then the P1 minus P2 is the pressure drop, the pressure difference. So velocity we got here. The equation we can use velocity equation. Then the volumetric flow rate we can always get. Volumetric flow rate you multiply with the volumetric flow rate into velocity into area, cross sectional area. So we always get from here volumetric flow rate of an orifice meter. So this equation we can use for to find the how much a volumetric flow rate in the pipe, this one. So there is a C naught you know that is orifice, this one, then A naught the orifice meter cross sectional area, then 1 minus beta power 4, the ratio, the diameter ratio, we called it diameter ratio, pressure drop, then density. So problem 1 we will discuss what is this one. The sharp edged orifice having diameter of 0.6 meter. The orifice diameter is the DO equal to 0.060 meter. That's orifice diameter. So installed the pipe. They install the pipe, but here the orifice meter gap is there. Orifice meter small. So the pipe diameter D 0.160, through which oil has a density. Oil density is there. Oil density already problem given. So 900 kg per meter cube. Then viscosity 4.1 centipoise. You convert the unit in terms of Pascal seconds or whatever, based on SI units, we can always change it. The measured pressure difference across the orifice. So the 85 kilopascal. So 85 kilopascal you convert in terms of 85,000 Pascal. Then the coefficient of discharge, the CO is we called as a coefficient of discharge. Orifice, this one, the CO 0.62. So all values are given already. The beta is the ratio, diameter ratio. We always write beta equal to D2 by D1. So what is the D2 here? That's the D2 is the orifice meter, orifice diameter, then divided by the pipe diameter. So we call as the DO by D, pipe diameter. So then we got a value of 1 minus beta power 4. Then velocity through orifice, we know the equation, the previous equation already the equations are there, the V naught equal to here. So, we can use the V naught equal to, so V2 is the C naught value already given, the problems already given 0.62, then 1 minus beta 44 we got from here, then 2 the pressure drop in terms of Pascal, so that also given here. So, finally, we got the velocity equal to 8.6 meter per second, the velocity, the value V2 equal to 8.6 meter per second. So, once velocity done, the another part is the area is the by d2 square by 4, this is a orifice diameter, orifice we can say by d naught square by 4, orifice diameter already is there. So, then A2 from cross sectional area we got A2, then the volumetric fluid, if you want volumetric fluid we can always multiply with the area and velocity, because area is a meter square, then velocity is a meter per second, then we get always meter cube per second, that is called the volumetric fluid. Sometimes they may ask mass flow rate you multiply with the density kg per meter cube, then we will get the kg per second. So, we can get the mass flow rate, that is called mass flow rate. So, we can just you have to keep on change that one. So, here velocity, from velocity multiply with the area, then we can get volumetric flow rate. You multiply the density, then we can get from here mass flow rate, that is a mass flow rate. But the problem here given only to find the what is the volumetric flow rate here. So, the volumetric flow rate here 0.0243 meter cube per second. So, next problem again, the problem 2, the same type of problem, but little different here. Okay, and the brine specific gravity 1.15, that is a specific gravity, meaning the specific gravity of brine solution 1.15. Then the specific gravity of mercury also there, that is a 13.6, this one. The diameter of internal diameter of pipeline is a 12 centimeter and converted as finally in terms of meter. So, then their maximum flow rate is 1800, they already mentioned here, given the 1800 liter per minutes. That is the volumetric flow rate, because since liter is there, it is a volumetric flow rate. Sometimes if they give mass flow rate, we convert in terms of multiplying density and get the value of volumetric flow rate. The sharp edge orifice connected to a simple U-tube mercury manometer. Since we added mercury manometer, then we added the specific gravity of mercury, that is a 13.6 here. Used to be installed for purpose of measurement. The maximum the reading of manometer is limited to 30 centimeter. The manometer reading is 30 centimeter, that called 0.30 meter, 30 centimeter. Assuming the orifice coefficient is 0.64, orifice coefficient is 0.64, then calculate the size of the orifice, that is meaning the diameter of orifice they are asking. Okay. So, all values are given already, the diameter is there, then flow rate is there, then specific gravity also available, the manometer reading here, the coefficient of discharge also here. First Q equal to 1800 liter per minutes, that we have to convert in terms of SI units, meter cube per minutes. So, Q here 1800, then convert in terms of meter cube, because 1000 liter equal to 1 meter cube, convert a meter cube, then if we convert in terms of seconds, the minutes to second. So, then finally we done this one, the Q value is 0.03 meter cube per second. So, you want to convert density, because the problem already given, the values are 1.15, the specific gravity of brine solution. So, then we have to convert in terms of multiply the density, multiply the value, then we get the value of density here 1000. So, finally, the density of brine solution is 1150 kg per meter cube. The density of brine solution is 1150 kg per meter cube, because the problem already given the specific gravity. So, the pressure difference here, we know pressure difference, we can always write P equal to rho g h. This already we derived so many times. So, there is here the density difference are there, one is a mercury density difference, other one is for the rho f. Rho f is the brine solution. density of brine. We can write even B also to understand. Okay. So the density of mercury, that 13.6, the specific gravity already given value, you convert in terms of density 13600 here. So then this value you substitute, and then there is a brine solution value also there, 1150. Then we know the gravitational, this one G equal to value, then the height of manometer reading, already the problem itself given, the height of the manometer reading, H value. So where exactly this one, 0.30 meter. So once 0.30 meter, then we get the value of pressure drop, that's called delta P, pressure drop. Pressure drop is the 36640 Pascal. So the pressure drop done, then we know what is the velocity through the orifice meter. So the orifice meter here, the V naught equal to the C naught value also already given, the problem itself given, 0.64. Then the pressure drop already values are there. Then the density of brine solution is here. So then we got V naught. What is the V naught? V naught is the 5.11 meter per second. Here we have to use the density of brine solution, not in the mercury, because since that solution only we are passing through the pipe. So we should not use some other here. Okay. So once the velocity done, now we got to calculate velocity. Then volumetric fluid, we know already volumetric fluid from the previous, this one already given, the problem itself given volumetric fluid. Then from here we got velocity. Then finally we can get from area, A naught. So the A naught here 0.0518700587 meter square. That's a cross sectional area of the orifice meter. So the orifice meter, the cross sectional area A naught. So once A naught done, then we know the cross sectional area equation, A naught equal to pi d naught square by 4. By d naught square by 4, that's a d naught orifice diameter. So then calculate d naught equal to, the finally we got d naught equal to orifice diameter is a 8.64 centimeter. The problem itself they asked. The first problem they asked what is the flow rate they asked. But the second problem we have to use the orifice diameter. But very careful, the density we have to use very carefully. We cannot use the mercury density here. We have to use for whatever the solution, whether water you are passing, what is the fluid, what type of fluids are you using, that type of only we have to use here. So next one is a flow nozzle meter, that is a flow nozzle meter, another one. This also we can use for always use the differential pressure to measure the flow rate of the liquid, gases and the steam via pipes. So as the fluid travel from through smooth surface, then the velocity increases and the pressure decreases. So the flow rate, how you have to calculate? Normally the flow rate is calculated with the pressure difference. That's the pressure difference, the P1 minus P2. So you want to calculate permanent pressure loss, that's the P4, that's the lost portion, where exactly final, the P4 is the exactly final, the lost point. So the P1 minus P4 we can write 1 minus of beta square by 1 plus beta square P1 minus P2. That is called the, we can measure from here pressure drop through this one. So that's called a flow nozzle meter, and again the figure here given here. So next is a rotameter. The rotameter we called as a variable area flow meter. The variable area flow meter, you just see here the area is getting variation. The area getting variation. So we called as a variable area flow meter. So that measure the volumetric flow rate. Measure the volumetric flow rate. What is the volumetric flow rate here? Meter cube per second. Volumetric flow rate of a gases or liquids by allowing whatever the fluid inside to lift the buoyant force within a tapered vertical tube, that whatever the tapered vertical tube that place. So rotameter maintains a nearly constant pressure drop. They always try to maintain the constant pressure drop even while the cross sectional flow area varies with the flow rate. Even if you vary the flow rate, but try to maintain the pressure drop throughout this one constant pressure drop. So here this the figure given here rotameter, there is an inlet, and then this called as a float. This one is a float. You can see here float, and then it always, you just pass through the fluids here, then it will come as an outlet here, and this outside is the annular of flow, this one, annular of flow here. Yeah, that's only. And the plate is, this one is the outside, it's a very transparent tapered glass tube. So we can always see what is happening here. So the rotameter we always call as a variable area flow meter. This is a different variable area flow meter. So area keep on change here. So the rotameter, normally the variable area flow meter is formed as a clear glass plastic tube that is tapered vertically and free moving float inside this space, okay. And here it's a free moving inside, but it's like tapered tube, but we can see visibly. So it's very clear of glass, clear glass, and then or plastic tube also we can use. The float rises inside the tapered tube, that's inside tapered tube is rising, the float is rising here as the fluid. When you pass the fluid here, say example here, when you pass the fluid, then the float is rising, the float is getting rise until the buoyancy forces, then the drag force, then the float weight, what is the weight that balance each other, and the net force acting on the float is a 0. The net force should be acting as a 0. So simply comparing the float position to the graduated flow scale outside. Outside there is scale is there. The tapered clear tube, it gives exactly what is the flow rate, volumetric float here. The float may be spherical, or the loose fitting piston like cylinder, whatever, okay. And this is a very important point. The float has a higher density than whatever the fluid you are using, because that is very important. The float should be has a higher density than the fluid, then only we can use here. So this is a rotameter. So it's a very we can see here the tapered, the vertical tube here, and we call it as a float. So when you pause this one, then it's automatically get float here. So we can always see in the outside. So another point, the annulus created between the float, there is a float and tube ball is there. Where is the tube ball? I will show you. This is a annulus and then is a float. This is a float. Okay. So the annulus created between the float and the tube ball, the space for the flow. There is the flow is occurring only that point only. The area of the annular gap, between the float is and the tube changes when the flow automatically changes, because the float rises. So the float rises, flow increase, expanding opening area until the differential pressure barely balance the float weight. The advantage of rotameter, what is the advantage of rotameter? Directly we can visual a reading of that one and nearly linear the scale. Okay, wide range, and directly we can visual the reading of this scale. So these are three different type of drag forces here. There is a vertical position of the float is established by three forces are there. One is the gravity force. The gravity force always acted downward. That's called a downward force. That's the force mass of the float here. Then another is a buoyancy force. That's always act as a upward. So upward force. So due to the displaced by the fluid volume. Another drag force is there. That's a drag force here. Drag force also upward force. It's by the kinetic energy and also shear stress of the rising of the fluid stream. To understand, we shown here how the establishing three type of forces are involved. So one is the gravity force, other one is the buoyancy force, the finally is the drag force. That's a drag force. So again same basic Bernoulli equation principle, the pressure drop, we always use the first pressure energy P by rho g, then V square by 2g kinetic energy, then other one is for mg is a potential energy. So then automatically this will get cancelled. So only we are playing with only pressure energy, then velocity here. So the pressure drop rotameter results from both the conversion of pressure energy, that is the pressure energy, to kinetic energy and friction loss. So all you have to take, and coefficient of discharge also. So, the continuity equation we know there is a rho 1 also here, but we will get a cancel, then we get A1 V1 equal to A2 V2. So, what is A1? A1 is the cross section of the tube, then A2 is the cross sectional annulus, the area between the tube and the float. That is here, that is the difference here. So, after modification, then we got the V2 equal to in terms of this one. So, here we are using as it is A to A1, we are not changing as in terms of D to D1, the area we are keeping as it is. Since area changing, then the area we are keeping inside as a area. The previous problem, diameter changing, so that is only diameter we are here, diameter is not changing, diameter we are keeping, but since area changing, so we are giving the area here. Since the upward force acting on the float balance the net downward force, so we can write delta P AF. So, normally force you can write P into A, we already know that one. So, there is a pressure drop and then this is the area of this one float here, it is called a FG, the FG here and FB. So, FG we can write mg, so then replace the m equal to in terms of Vf rho f this one, and same way for FB also, FB here mg. So, that is a Vf rho g float. So, then delta P AF equal to the previous delta P AF, whatever the delta P AF equal to, we can write Vf equal to rho f minus rho. So, where is the rho f? Vf is the volume of float. What is the volume of float? Then the density of what? Density the floating material, density of float here. Then the AF is the maximum cross sectional area. We will use the maximum cross sectional area of a float, that one in the horizontal plane. So, finally, we can get from here delta P equal to the pressure drop equal to, from there we can get the value of this one, volume of float we know, then area and the density difference and then G. So, then the rotameter normally we calculate through Q value, this is a Q equal to CD, we called as a CD is a coefficient of discharge. But here the CD is the depends on the shape of the float, then the Reynolds number both together. So, the function of the CD is the mainly function of depend on the shape of the float, then the Reynolds number, we know Reynolds number already. So, then we derive that Q equal to 2 of Bf, the rho f minus rho g divided by this one. So, we will discuss the problems to understand, it is very easy. A rotameter which is stainless steel float is there and the maximum capacity of QW is there 2 liter per second and then 25 degree. What is the maximum capacity for the kerosene in terms of liter per second for the same rotameter and the same float? The rotameter also same, the float is also same. The specific data stainless steel SGF is there 7.92, then kerosene value is there, water is there. The kerosene value is specific gravity and here is the specific rate of water also here. So, after if it same rotameter and the same float, we can always use this equation, the modification of previous equation. So, Q2 equal to Q1, the Q2 is the flow rate of kerosene, QK we write kerosene or this you write QW water. So, again rho n, the rho 1 we are replacing in terms of specific gravity, because everything is same, because specific gravity here, then rho f is again specific gravity of F, then rho 2 specific gravity of 2, same by divided by same thing. Okay. So, we can write either this way or this way, but the problem already given in terms of specific gravity. So, we are going to use this equation Q2 equal to Q1. So, Qk equal to the 2.0 this value and then all values already given, then finally, we got a kerosene, what is the flow rate of maximum capacity of rotameter kerosene here 2.24 liter per second. Okay. So, now we will move to another problem, that is a last problem. Again the rotameter calibrated for metering has a scale ranging, the calibrated 0.0 to 0.02 meter cube minutes. The original flow range is the 0.0 to 0.20 meter cube per minutes and then the density is there, density is the 1.5 kg per meter cube. Density is 1.5 kg per meter cube. So, within the flow range, the range is there again 0.032 the new flow range. First is the original flow range, then the new flow is here 0.0 through 0.32 0.30 meter cube per minutes. The density of gas is there, density of gas is also already given, density of gas is 1.5 kg per meter cube, here already there 1.5 kg per meter cube. Then the density of original float, the values are there 2100 kg per meter. But what they are asking, what should be the density of the new float if it is original that one. So we can calculate here. So this is a standard formula, Qf equal to K into rho f by rho into 0.5. So then Q2 by Q1, the ratio of the two flow, one is the new flow and the old this one. So here new flow range, then old flow range. Then rho f by rho g this one. So Q2 by Q1 we get value of 1.5. So we know the value of Q2 by Q1 1.5. Then we know the density of the fold this one, the old one. Here density of old one we know. So then you just calculate, then finally we get the density of the new density of flow, the new one. So that's called 47723.125 kg per meter cube. So the different type of flow meters there. This is only just for turbine and paddle wheel is there. It's based on the wheel whose the rotational speed, that's the directly proportional to fluid velocity. Then there is a thermal gas mass meter also there. These are different type of flow meter. So this sensor, this one is for normally work for main steam as a parallel sensor tube using the constant laminar ratio. So this will give always definitely temperature and the pressure always fluctuation have the no effect on here this one. So another is a magnetic flow meter. This also we always use. It works with the Faraday's law of induction of this one. So here when the fluid move through the magnetic field, then we can measure here. It's independent of density or viscosity, but we cannot utilize in the non-conductive hydrocarbons. Another flow meter same way, it's a U-tube side channel, and again it works on Newton's second law. So again here highly resilient design and insensitive to change the fluid type, viscosity, density or slurry here. The last one is for vortex steady flow meters. This is also based on the, normally we use for the hydrodynamics fluid. Whenever the velocity is very high, then automatically lot of the vortices and eddies will form here. So another flow meter is a positive displacement flow meter here. This is also same way, the calculate the flow rates by dividing the fluid stream into accurate volume, then mechanical to move internal elements. So this positive displacement flow meter we always use frequently use the domestic, sometime industry line also. So for example, the gas and water meter. So we just different type of flow meter we discussed. We started with the rotameter and then previous one is orifice meter, and this is a general for discuss that one. Thank you.